So welcome to Verilog HDL. So module 3, that is gate level modeling. So after seeing what do you mean by gate level modeling and how to instantiate the gates, okay, so how to instantiate gates and gate types. Okay, in gate types we have seen one is and or gates, one more is buff bar not gates. Okay, so buff bar not gates and or gates we have seen, and we have seen truth table with respect to those, and how to instantiate the gate means gates. For example, gate and is keyword and n1 is instance name, and if output is c and inputs are a and b, so we will declare this, we call as and instantiation. Okay, so here, so after seeing gate level modeling and uh, the gate types and instantiations, so all those things, so by learning all those things, so we will see some examples, means how to design the circuit and how to write the code with respect to gate level modeling by taking some examples. Okay, so here the first one, the what the example means, we are seeing here the 4:1 multiplexer. Okay, so already we know what is multiplexer. So multiplexer, so here 4:1 multiplexer we have considered. So basically the multiplexer is the one which will pass the input to the output based on the select lines. Okay, so as we are saying the truth table here, if the select lines are 0 0, the output will be assigned to, means the output will be assigned to I naught. Okay, or I naught will be assigned to the output. If the input is 0 1, then I1 will be assigned. If the input is 1 0, I2 will be assigned, and input is 1 1, then I3 will be assigned. So depending upon the select line, any one of the signal, input signal, will be assigned to the output. Okay, so this is the working of the multiplexer. There are 4 inputs and 1 output here. Okay, so how to write the gate level modeling for this 4:1 multiplexer? Okay, so as we know, the gate level modeling means the input should be the logic circuit, means it consists of gates. Okay, so now as we know, in the gate level modeling we need to have the logic circuit. So based on the truth table or based on the Boolean equation, so we can design, so based on the truth table we can design the logic circuit. Okay, so this is the design of logic circuit. We are not bothering here, because for to write the gate level modeling, the Verilog modeling, we need logic circuit. So that, so directly we are seeing now the logic circuit. Okay, so these are the 4 inputs, 4 data inputs, and these 2 are the select lines, and out is the output here. Okay, so if the select lines are 0 0, so both are 0 0, so this will become 1 1. So this both are 1 1 is connected to the AND gate, and if both are 1 1 here, so the third input, means the I naught will decide what is the value of Y naught. For example, if I naught is 0, okay, as both are 1 1, the output is 0. Suppose if I naught is 1, as both are 1 1, so the output will be 1 here. Okay, so similarly, if you take other combination, for example, if you take 0 and 1, okay, if you take 0 and 1, so 0 means, so this will become 1. Okay, so this 0 is connected to what we can, 0 means if you see the truth table, so if you see the truth table, 0 1 in the sense we are considering S naught as 0 and S1 as 1, the third combination 1 0, S1 is 1, S naught is 0, means I2 will be selected, means the third gate here. Okay, so if you see here, okay, okay, so if you see here for the combination, if you see S1 and S0, if S0 is 0, S1 is 1 for this combination, means the S0 will be 0, S1 will be 1. Okay, so if you see the Y2, the third combination, if it is 0, Okay, for y2 this will be 1, and for y2 the second input, okay, so directly connected here, so directly 1 1, one is directly connected, one is inverted, both are 1 1. So whatever I2 value, so that will be represented by y2 here. Okay, so for this combination, if you see the y1, okay, if you see the y1, you can see here, okay, so here y1 is connected with the knot of this, so as it is 1 and this will be 0, if any one of the input is 0 means the y1 is 0 here. Okay, so it will not based on the I1, the y1 output is not based on the I1 when the inputs are means S1 is 1 and S0 is 0. Okay, so like this what will happen, if the S0 and S1 are 0 0, the y1 y0 is means the whatever y0 is that depends on I0. If select lines are 1 and 0, the y2 is depends. If it is 0 and 1, the y1 is depending on I1. If it is 1 1, so y3 is depending on the I3. So rest of the cases means respective, if y1 is dependent on I0, others will be 0, means other outputs will be 0. Okay, so this is how according to the truth table the multiplexer circuit will work. So for this one, how to write the coding is, how to write the gate level modeling. Okay, here first we need to see how many components are there. Okay, so here 4 AND gates, 1 OR gate and 2 NOT gates. Okay, if you see here how many gates, 1 2 3 4 AND gates, fifth one is OR gate, and sixth and seventh one is a 2 NOT gates. So totally there are 7 gates are there. Okay, so now let's go on writing the gate level modeling. So here, as we know in Verilog modeling, Verilog HDL, the module is a keyword. Module is a keyword, that is a must. After that, module name. So here module name they have given as 4 is to 4 underscore 2 underscore 1. So one more thing, what we need to remember while giving the module name, there should not be any space. For example, it cannot be mux space then again 1. Okay, so we should use the underscores. Okay, so module is a keyword and this is module name, and these are inputs and outputs. And one we need to keep in mind in gate level modeling, as we said earlier, so output we should declare first. So there is only one output, so out is declared first, then declared in the sense out is mentioned first, so after that inputs, so 4 inputs and 2 select lines. Okay, so this is how we need to start the module keyword, module name and port list. So once we write on this and last the semicolon after the parenthesis. So now after writing the port list, then we need to declare which are the inputs and outputs. So output out. Okay, so the output is again the keyword here and out is the variable. So as it is scalar, means it is only one bit, so no need to write like 1 down to 0, 2 down to 0. So that will come when the inputs and outputs with the vector value. When it is more than 1 bit, then we can declare like this. If it is 2 bit, like this, and if it is 4 bit, then it is 3 down to 0. Okay, so like this we need to declare the inputs and outputs. So all are it is single bit, so out, output, and input I0, I1, I2, I3 all are separated with commas and last semicolon, and the last one select lines, input S0 and S1. Okay, so here even in the same second line we can write S1 and S0 with I0 to I3, but just to understand better, just we are taking the another line. Okay, so we can include in the first line, second line itself. Okay, so as select lines also inputs. So after declaration, so we need to define, so which inputs and outputs we can declare as wire, means basically we are mentioning the data types here, whether is it reg or wire. Okay, So one thing we need to see in gate level modeling, so all are wires only, because we are not storing any, the combinational circuit will not store any values. Okay, so as the logic circuit what we are seeing at present for 4:1 marks, okay, so it don't have any memory element, so we will declare with the all are with wire only. Okay, so no need to declare the inputs, no need to declare the inputs, uh, means I0, I1, I3, so that is what is that, so those things are the optional. And if you see the circuit, mm, yeah, if you see the circuit here, yeah, if you see the circuit here, so what are the inputs and outputs here? I0 to I3 are inputs, out is output, and S0, S1 are the inputs here. So these are inputs and this is output, and what the signals what we are seeing inside the dotted line. Okay, inside the dotted line what we are saying Y0 to Y3 and S1n and S0n. So these we call as intermediate signals. Okay, these we call as intermediate signals. Okay, so these signals must we should declare as wire. Okay, as we said earlier while explaining data type wire, so intermediate the wire will be used to declare the intermediate signals. So in this module, in this circuit, Y0 to Y3 are intermediate signals, and S1n and S0n are the intermediate, and these are inputs and this is output. Okay, so now, okay, so while writing the code, the internal signals, that is S1n and S0n and Y0, Y1, Y2, Y3, all these things we must declare as wire, that we are declaring. Okay, with respect to inputs and outputs, so as it is the logic circuit, means the combination circuits, no elements are there, no memory elements are there, so no need to declare outputs as register. So default it will take as wire. Okay, so now this is input output declaration, this is data types, any intermediate signals we need to declare. So then we need to write a code now. So as I said earlier, we have 7 gates. Okay, we have 7 gates, 2 NOT gates and 4 AND gates, 1 OR gate. Okay, let us start with NOT gate. So NOT is a keyword. Okay, NOT is a keyword, and okay, one more thing, instance name they have not used here. Okay, so as the signals are the different, okay, as the input and outputs are different, so it doesn't matter here. So if instance name is not there, so it is better to give the instance name. For example, if the circuit is like this, I can give instance name as N1, N2, N3, N4, okay, N5, N6 and N7. Okay, by using this instance name, okay, so I can know that there are 7 statements are there. Instead of seeing the statements, so directly by seeing this number, I can know that how many statements are there, and we can differentiate easily with a instance name. Okay, so otherwise we need to see the signal names. Okay, so okay, here instance name is not there, but it will work. It is better to use the instance name. Okay, the first NOT gate, and here the input is S1, output is S1n, means if the gate is like this, input is S1, the output is S1n. In that case, first we need to declare, mention the output, then input. Similarly, the next NOT gate, S0 is input and S0n is a output here, that what we are declaring here. Okay, so these 2 NOT gates. Then if you come to the AND gate, first AND gate, so Y0 is output, that is intermediate signal, and what are the inputs for that? So input for that is I0, that is from main input, and S1n and S0n. So whatever the outputs generated by NOT gate, okay, whatever the outputs generated by NOT gate, so that is connected to the AND gate here. So like this, and this is I0, okay, and the output of this is Y0. Okay, so y naught we need to write first, then inputs, that is I naught, okay, s naught and s1. Okay, sorry, here s naught n, s1 n for this AND gate. So these are the inputs, s naught n, and s1 n. Okay, so this is how we need to instantiate the AND gate, first AND gate, similarly second, third and fourth. So these are the outputs and these are the inputs. And the last one, okay, for that, okay, so all OR gates means, sorry, all the y0, y1, y2 and y3 generated by AND gates, so that will be given to the OR gate, and this is a output. So the output, main output will act as output for OR gate, and y0, y1, y2, y3 will act as a inputs for OR gate here. Okay, so this is how to write the gate level modeling. So we should have we should have the logic circuit, we should find out how many gates are there, then that many statements will be there, and we need to declare what are the intermediate signals with the data type wire here. Okay, so we need to use the names which are different from the whatever inputs and outputs. Okay, we should not use the same names. Okay, we need to use different names what we have used for inputs and outputs. Okay, so this is how we need to write the gate level modeling for 4:1 mux. Okay, let's look at the how to write the stimulus block means. So whatever we have written the block here, this we call as design block. So in the very first module, we know in the Verilog modeling we have design block and stimulus. So design block is the one what actually required the design means, for example, for 4:1 mux we need to write the code, so that is a design block. So stimulus block is the one from which we will test this design block by giving the inputs in the stimulus block. Okay, so stimulus block for this 4:1 mux, okay, 4:1 mux stimulus block, it start with module. So it is like this only, this is a design block and this is a stimulus block. Okay, 4:1. Okay, so whatever the outputs here and whatever inputs here, it will be generated by stimulus block internally, and the outputs will be observed in the stimulus block. So stimulus block itself don't have external the signals which are connecting to other module. Okay, don't have that. So because of that, only stimulus, no port list as they are given, no ports. And here, so as I said, so whatever for the design block, whatever the inputs we are using, so that must be declared as register in the stimulus block. Okay, whatever the inputs, what inputs we are using for 4:1, that is I0 to I0, I1, I2 and I3. So these and S0 and S1. Okay, so these must be declared as register. Okay, and whatever the output of design block, that is out, so that will be declared with the wire, but we need to use the different names. Okay, so instead of there we used the smaller letters, and here you are used the, as the Verilog is case sensitive, so we are using capital letters IN0, I1, IN2, IN3 and capital S0 and S1, and here capital output. Okay, so now after declaring, so as I said, we need to remember the outputs of design block we need to declare as reg, and inputs of the design block we should declare as reg, and output of design block we should declare as wire. So after the declaration, so this is the common method to write the procedure to write for any design block. Declare the module with the module name with no ports, then declare inputs as reg, output as wire, and here we need to instantiate the whatever the design block. So design block module name is mux 4_2_1. So this is the module name of the design block what we have used in the design block. Okay, this is the instance name, so anything we can give, but this must be the module name. We need to enter what you have used in the design block, and here the module output Okay, so as I said, the instantiation is of two types, one is by order, one is by name. So here we can see the order, first output is there, then 4 inputs are there, then select lines are there. If I am using the same order, okay, same order, this is one of the method. Okay, name means first output is there. If you want, you can see that you can see here the order, first output, then inputs, then select lines. Okay, so in the same order what we are declaring here, output, the input names, the input that is I0 to I3 and select lines. Okay, but name should be the what we are declaring here, that we need to mention. So after declaration and instantiation of the design block, now we should start with initial. So initial is again a keyword. Okay, so initial is again a keyword. Initial, after initial, if it is only one line we are using, then no need to use begin and end. Okay, if we are using more than one statement, then we need to write begin and end. So after the initial, begin and end, within begin and end we need to give the inputs. Okay, that we call as the initial block. Okay, this is one block, initial block. Okay, so now after the begin we need to start giving the inputs. How to give the inputs? So whatever the input variables you write down, in0, in1, in2, in3 and in0 equal to, so how many bit that input is, all are single bits only. Okay, so I am directly using in0 equal to 1 or in1 equal to 0 and in2 equal to 1 and in3 equal to 0. Okay, so now here after writing each one we need to give the semicolon, we need to use semicolon. What we are saying here, the semicolon we need to write. Okay, so in0 give the value, in1 give the value, and after that use the semicolon for each statement. Okay, so after giving these values, okay, after giving these values, I need to know, during the runtime I need to know the what values I am giving, I need to see on the screen. Okay, for that purpose I am using $display, which is the system task. Okay, and #1 is the delay. You can give anything, we can give #10, #100, #5, whatever the value we can give. Okay, so here they have used #1 means the after means these all values will be assigned to the respective inputs. After assigning that, after 1 nanosecond, okay, the nanosecond is the default what it is in the tool. Okay, and we can change the units also, so default it will be nanosecond. So #1, okay, after the delay I want to print these values. How to print? By using the system task, and here $display in the bracket, okay, the double quotation. So in the double quotation, so what are the variables? in0, and what is the format, in which format I want to display, is it in decimal, binary, hexadecimal or octal? So this is %b is binary, comma, in1 equal to %b, comma, in2 %b, comma, in3 %b. Okay, so this \n is next line, and here is the format. So $display, double quotation, and write down the variables with string format what we need to represent the type. After that, once it is double quotation and comma is over, then we need to write the variables in the sequence what we have written. Okay, in the sequence or the variables what we have used here. Okay, I0, in0, in1 with a separated by comma, and last close the bracket and semicolon. Okay, so the first line will assign the values, second line will print, not now, during the runtime. Okay, the next, okay, I have given the inputs now, not only I0 to I3, I have select lines also. Okay, so initially I am giving 0 0, means what is the job of multiplexer? If there are 4 inputs are there, based on the select, if it is 0 0, first one will be select. So I am giving 0 0, and again I am displaying the select lines S10 S10 and S00 I am giving, and given delay, and given the formats I want to represent S0 and S1 values in binary, then I want to see output. Okay, so output is, again, this is variable in the format %b, and these are the variables what I am using in this particular statement. Okay, so after giving delay, okay, I am displaying the S0 values and also the output. Means when the output will come, I need to give these values and I need to give the select lines. After giving select lines, the output will come. Okay, so similarly, so next is, so here choose I0, means how to choose I0? By selecting S0 and S1 as 0 0. Next, choose I in 1, how to choose? By giving 0 1 value. How to choose I in 2? By giving S1 1 0. How to choose I in 3? By giving 1 1. So step by step, first I am choosing IN0, okay, after that I am giving delay IN2, IN1, IN2, IN3, okay, and I am displaying all the values with respect to each one by using the system task $display. Okay, so after giving all the pattern is over, there are only 4 combinations, all the 4 combinations are over. Initially I have given as inputs constant. Okay, so now this is the end, and last is end module. So whatever the module you have started with stimulus block, that is ended with the end module. Okay, so this is how we need to write the stimulus block. Okay, and this is what the design block, and this is a circuit, and this is the problem, the 4:1 multiplexer. Okay, so now this is the output values, how it will see. Okay, so how many $display statements we have used? We have used 5. In the first one, it will display I0 to I3 values. In the second one, if the select lines are 0 0, what is the value of 1? 1. Why it is 1? Because I1 is 1, because when the S0 and S1 are 0 0, so I0 will be connected to the output, so I0 is 1, the output is 1. When it is 0 1, I in 1 will be connected, I in 1 is 0, output is 0. When it is 1 0, I2 will be connected, so in 2 is 1, so output is 1. So when the select lines are 1 1, I in 3 is 0, the output is 0. So this is how the $display will be used to display the values, and it will be only one time. So at that instance, means what is the meaning of that is, okay, if I am using $display here, means at this time what is the values, what is the status of variables, only it will display at this time. Okay, again at this time other statement we need to use, again at this time again we need to use this time. Means at different times we need to know, means we need to use the 4 different displays if I want to know the changes what happened. If I use display, I need to use like this. Okay, suppose with one statement I need to see what are the changes will happen by writing only one statement, then I need to use the $monitor instead of $display. If I use $monitor, at last if I use $monitor, and if I use all the variables inputs and outputs, no need to use that 4 monitor, only one monitor is in it, because any change with respect to any time with variables, it will display. Okay, so this is what the difference between the $monitor and $display. $display, it will display at particular time. Okay, it will not update. Okay, but monitor will update at every time, and it will display all the values, what are the changes occurred in the variables. Okay, so these are the outputs with respect to 4:1 multiplexer. And the next one, we will take one more the example, that is 4-bit full adder. Okay, so now the 4-bit the problem is the 4-bit full adder, but the whatever circuit we are seeing is 1-bit full adder. Means What is the difference between 1 bit full adder and 4 bit full adder? So 1 bit full adder means I am assigning, for example, A, B, C, and sum and carry is output, and here it is full adder. Okay, the A, B, C are of single bit. A is single bit, B is single bit, C is single bit, and the full adder, it will add and give the sum and carry. This we call as 1 bit full adder. Okay, similarly the 4 bit full adder means, okay, so you'll see next also, the 4 bit full adder means here, okay, so 4 bit means the A will be 4 bits like 1011, and B will be 4 bits 010 like this, but C, anyway it is carry, it is single bit. Okay, that is C in and C out. The third input will be the carry, single bit, and these two will be single input for this one. But when we take for overall together, okay, it will be like A0, A1, A2 and A3. Okay, so this is A0, A1, A2 and A3. So individual bit will be assigned to each full adder here. Similarly, B0, B1, B2 and B3. Okay, so here like this, the 4 bit full adder will take input as 4 bits, and 1 bit it will take input as the 1 bit here. Okay, so for 1 bit full adder, this is the equation, Boolean equation for sum. This is the equation for C out, like C out and sum, and there is a small correction in this circuit. So this all these pictures I have taken from the textbook. Okay, so it is not the XOR, it is OR only. Okay, it is OR only here. This is OR gate, not the XOR gate. Okay, so whatever this gate what we are using, so this is OR gate, not the XOR, and so in the book it is by mistake it is printed. Okay, so as you can see here, the 3 inputs, 2 inputs XORed, and output of that is again XORed, that is this one, or XORed with a C in, that is A XOR B XOR C, that is what sum. Okay, if you come to the carry, A dot B, okay, A dot B and A, S1 is A XOR B, so A XOR B, okay, A XOR B ANDed with C1, A XOR B ANDed with C1, C in, that is this term, and one more is A dot B, that is this term, and both are added, so this is OR gate here. Okay, so this is what the circuit, logic circuit for 1 bit full adder. Okay, and how to write the code for this. Okay, so as I said, the 4 bit full adder is nothing but using of the 4 1 bit full adder. So this is full adder, this is full adder, this is full adder, this is full adder, so each of 1 bit. Okay, each of 1 bit. So for that, first we need to write code for 1 bit full adder, then instantiate 4 times. Okay, the same thing here, the 1 bit full adder circuit. Okay, for this we need to write the code. So because of that, you can observe here very first line, Verilog description for 1 bit full adder. Okay, so this is a module, is a keyword, module name is full adder, and as it is 1 bit full adder, 3 inputs and 2 outputs. So outputs we are declaring first sum C out, inputs we are declaring second A B C in, and this is the size of the declaration of inputs and outputs, that is sum and C out, and inputs A B C in. So all are single bit, so no need to use the brackets, so directly we can use output sum comma C out and input A comma B comma C in and semicolon at the last. Okay, then yeah, these wires, so wires how we need to declare, so what is the based on that, so this is what wires is required here. So S1 is intermediate signal, C1 is intermediate, S2 is intermediate, means we are not seeing outside this dotted line, these outputs. Okay, so these S1, C1, C2, S2 is the intermediate signals, those must we need to declare as wires. Okay, so the same thing what we are doing here. Okay, so here S1, C1 and C2 we are declaring with the wires here. And okay, now after declaring all those things, so how many gates are there? So totally there are so how many gates? So 2 XOR, 2 XOR, 1 AND, okay, 2 AND, okay, 2 XOR, 2 and 1 OR last. Okay, so here the first XOR is like A, B, I am giving it to XOR, which is output is S1, that is the first one. The next one, okay, the same AB I am giving into AND gate, okay, that is C1. AB the same thing I have tapped and given, so AB is input, C1 is output, C1 and S1 are declared as wires. Okay, so this is the two instantiation, XOR and first pair. Okay, the next one again XOR. Okay, in that case it is like what the circuit we have seen, again XOR here, this is S1, this is AB, okay, and the scene is connected here. Okay, so this XOR is, so this is sum output, so sum is output and S1 is input, one of the input, and scene is one more input that we have declared, and again here AND is there, one more AND is there, for that AND, okay, C2 is output and S1 is connected here, so one of the input, and the scene is again connected, it is second down input. Okay, scene and it is S1 and C2 is the output, so that is one more AND gate is over. The last is, okay, so last is OR gate. Okay, this OR gate output is C out, C underscore out, what we have declared here. Okay, and C2 C1, so output of AND gate, okay, and output of the first AND gate and second AND gate both are given as inputs like C1 and C2, what we have declared as wires, and that will be given to the OR gate, okay, and output as C out. So now how many gates? Totally there are 5 gates are there, 2 XOR, okay, and 2 AND gates, 1 OR gate. So this is one pair, this is one pair, and this is OR gate. Okay, this is how we need to write the only thing is instance name is not there, but we can write that one. Okay, so this is how we need to write the code. So individual component we need to take and we need to see what are the inputs and outputs of that. If it is intermediate signal, and use whatever we need to declare in the wire. Okay, so this is how to write the design block with respect to 1-bit full adder. Okay, so it is not complete code for 4-bit full adder, we have written only for 1-bit full adder. Okay, so now how to the 4-bit full adder, how it looks like? So as I shown earlier also, so it is F0, FA naught means full adder 0, full adder 1, full adder 2, full adder 3, means the scene is single bit, means this is a scene. Okay, so A naught, B naught, A of 0, B of 0 means the first, means as I said earlier, A means, or here we have taken as small letters, so A is input means 4-bit means 1 0 1 1 means this is A of naught, this is A of 1, and this is A of 2, and this is A of 3. Okay, so the first bit will be assigned here. Okay, the first will be assigned here, and similarly like B, okay, similarly like B we have 4 bits, so like this. Okay, so like this the first bit of both numbers it is assigned to first full adder. Similarly the second bit is assigned to second bit full adder, third bit full adder, fourth bit full adder. This is similarly sum as S0, S1, S2, S3, like sum of 0 1 2 3, and carry will be single bit. single bit input, single bit output, like that last Cout will be there. Okay, so this is what the 4-bit full adder, the circuit. Okay, the 4-bit full adder circuit have the components 4 full adders, 1 bit, this is 1 bit, 1 bit, 1 bit, 1 bit. Okay, so already we have written 1 bit full adder the previously, so that we need to call here, that we need to instantiate here. So the 4-bit full adder here. Okay, so here what is the name, what you have given? Full add. This is the module name for the 1-bit full adder. So we need to use the same name to instantiate. Okay, so full add, and here we are using the instance name, that is fh0, and what is the first full adder output? That is sum of 0. Next, what are the input? First we need to declare outputs. Sum is output and C1 is output. Write the C1, and A of 0, B of 0 and Cin. These are the inputs for first full adder. Okay, so if you see these diagrams, C1, C2, C3 are the intermediate signal declared as wire, and module is a keyword, and for 4-bit full adder module name is full add 4, and sum, Cout and ABC in. Okay, and here you can see the declarations. Sum is 4 bits, Cout is single, and AB are 4 bits. So as both A and B are 4 bits, so I can declare A comma B. Okay, when both dimensions are same, I can declare in the single line. And one more input is Cin. So this is declaration with size, and this is the data type, intermediate signal C1, C2, C3 we are declaring as wire. Then after that we need to write a code for full adder, means already you have written code for 1-bit full adder, just call them. Okay, just we are calling the first one and assign the proper signals, sum of 0, C1 and these 3 inputs. For next 1-bit full adder, sum 1 is the output and C2 is the output and A1. So A1 is the, so as we are saying here, the A1 and B1 will be the input, and as a carry input, the output of the first full adder, like C1, the output of first C1 will act as input for 2nd bit full adder. Similarly, the output of 2nd bit full adder will act as input for 3rd bit full adder, and 4th bit full adder, the C3 will act as a input here. Okay, so finally the output is Cout and sum 3. Okay, so this is how to write the gate level modeling for the, or structural modeling for the 4-bit full adder. Okay, so 4-bit full adder circuit is, so this is the circuit for 4-bit full adder, and these have 4 components, 1, 2, 3, 4. So these are the 4 components, and each component code we need to write. So the 1-bit full adder code is same, what you have written, the same thing we are calling, only we are sending the what, the signals we are sending the different. Okay, so it is nothing but there are 4 modules only, the instance name is different, there are 4 modules with a different names. Okay, so this is how we need to write the gate level modeling for 4-bit full adder. Okay, so the next is similarly writing the stimulus block. Okay, stimulus block is same what I have explained, the input whatever A, B, C in we need to declare it as reg, and output sum and Cout I need to declare it as wire, and this is instantiation of full adder, but we need to check the full adder now, sorry, 4-bit full adder, not the 1-bit. So okay, 4-bit full adder we are writing, so full adder 4, module name, instance name, so this is the same order what we are using, sum, Cout, ABC in, and here okay, that's what I have told here, instead of display we are using monitor, so only one time is enough, monitor $time A, B, Cin, Cout and sum. Okay, so all we are writing in single line, So dollar time is required. So dollar time will update the time with respect to the simulation during the running. So as the time changes, this will execute, and at particular time what are the values it will display. Okay, so how to give the inputs? Like I said earlier, initial, use begin and end. In that, give the value of a, b and cin. So a, how to give the values? A equal to number of bits is 4, a is 4 bits, tick. Okay, and d is decimal, value is 0, means I am giving decimal 0, means 0 value I am giving, assign it to a. Okay, suppose if I want to assign 5, then you assign, instead of 0 I can assign 5. So what is the format here? A equal to number of bits 4 dash. If I write b binary, then I need to write like this, 4 zeros. Okay, so I am using decimal, so I am using directly 0. So this 0, scene is 0. After hash 5, after some delay, I am changing the inputs 2 and 5. After some time, I am changing again value. Okay, after that again I am changing. So 1 2 3 4 5 6 times I have given the inputs with the delay. So I will show you in practical, we will see why delays are required. Okay, if delay is not there, only the last statement will execute. So actually all statements will execute, will not be visibly, we will not see due to the no delay. If delay is there, you can see the results. Okay, these things will be more clear when you start the practical. Okay, so here this is what the 6 times we have given the inputs. Okay, so what will be the output here? So output, what we are saying here, how many times we have given? So 6 times. So 6 statements are there. So 1 2 3 4 5 6. Okay, due by using because of I am using the monitor here. Okay, so whenever the changes, so initially 0 time. Okay, the values what I am displaying in binary, so 0 0, scene is 0, so output will sum is 0, sum is 0, carry is 1. If I am giving 3 and 4, this is in binary, 3 and 4 in decimal, 3 4, the value is sum is, carry is 0. If I am giving 2 and 5, output is 7, carry is 0. And if I am giving 9 and 9, okay, so 9 and 9, carry will be generated, and here it is 2. So it is 1 0 0 1 0, means this is nothing but 16 plus 2, that is 18, that is nothing but 9 plus 9, that is 18 in decimal. Okay, so this is how the values are giving. These are the dollar time which will print the give the time that is displaying here. At each time, what are the value changes and what are the output changes, so this will display. So this is what the difference between the dollar monitor by using only one time. Otherwise, if I would have used dollar display, then 6 statements I would have used. Okay, so this is how we need to write the stimulus block, the design block. Okay, and how to write the gate level modeling for the designs. So for that we need to have the logic circuit. Okay, this is logic circuit for 1 bit. Okay, then we need to instantiate. Okay, and here the earlier, so no instant means we need to write how many gates are there, so that many statements straightforward. Okay, and here the one module contain this circuit, and same module we are using, so instantiate, and whatever the function we are calling, so that particular code also we need to write. Okay, so this is regarding the 2 examples, multiplexer and adder, and how to write the gate level modeling.